Hello everyone, this is a follow-up to the previous pedigrees video that I made, and it gives some more examples of pedigrees and uses some of the questions, or provides a bit of a guidance to answering those questions in the homework booklet. So I'm going to start with question 6 in the homework booklet, which involves this pedigree showing the inheritance of the rhesus blood groups in a particular family. Now, if you read through the stem of the question, it gives away a lot of really important information. So, I'll say this all of the time, but remembering to read the full question is never truer than in these pedigree inheritance, or the inheritance being shown in a family with the pedigree. So if we read through, it tells us that the rhesus blood group is genetically controlled. So we can see on this little diagram, a person can either be rhesus positive with those antigens on the surface, or they can be rhesus negative without the antigens. So the gene for the rhesus group has two alleles. Allele for rhesus positive, capital R, is dominant to that for rhesus negative. Okay, so that's the first really important piece of information, that the allele for rhesus positive is dominant. Now, in your exam, you should be highlighting these things as well, or underlining it, really pointing it out. The second important part, it says that the diagram shows the inheritance of the rhesus blood group in one family. Is there anything? Yeah, and it also says later on that the evidence that there is, or you need to explain that it's not present on the X chromosome. So if you remember, in the notes on page 13, there are some really helpful tips, ways to prove that an allele is either recessive or dominant, or sex-linked or not sex-linked. Okay, then there's a little bit of extra information here, blah blah blah. So this is the pedigree. Just going to stretch that out a little bit. It shows, as all pedigrees do, squares for males, circles for females. If it's shaded in, sometimes we use this term affected. Now, affected isn't great really. Try to use, I think I've said this previously, try to use the context from the actual stem of the question. So in this case, shaded in means that they are rhesus positive, which I might abbreviate to that, and not shaded in means that they are rhesus negative. Okay, so we can see 1 is a male, rhesus positive, 2, female, rhesus negative. Now, in the stem of the question, it tells us that the rhesus positive is dominant to that for rhesus negative. The first question, explain one piece of evidence from the diagram which shows that the allele for rhesus positive is a dominant allele. So if we refer to page 13, it will tell us that if we want to prove that a allele is dominant, okay, we need to look for a situation where there are two, what I'm going to refer to as affected, or in this case, two rhesus positive parents, and they produce an unaffected, and again, unaffected is not great, but in general terms, unaffected, so rhesus or unaffected children or offspring. Okay, so we can see in this pedigree that 3 and 4 are both rhesus positive. Okay, they've got the shaded in circles, 3 and 4, both rhesus positive. They produce 2 offspring, 7 and 9, who are rhesus negative. So you will also see on page 13 that if we find that, the explanation for that is that both parents must be heterozygous. So I'm going to use R here to represent the allele. So 3 must be heterozygous, 4 must be heterozygous. And that means for 7 and 9, they have both inherited 2 recessive alleles. So the genotype for 7 must be homozygous recessive, and the genotype for 9 must be homozygous recessive. Okay, back to this question then. Explain one piece of evidence. Now, some questions will say give one piece of evidence, and if you are giving one piece of evidence, I'll do this in a different colour, so if it's give evidence, usually for 1 mark, if it would give evidence, you could just say 3 and 4 produce 7 or 9, and that will give you that 1 mark. Explain evidence, you need to go a little bit further, and I've sort of explained it already. Explain evidence might be 1 mark again, it might be more, but what we're looking for is the words. We need to say that the parents are heterozygous. Okay, so we have parents 3 and 4 are heterozygous, which means they both have 1 copy of the recessive allele, they both carry that recessive allele. And that recessive allele is passed on to 7 and 9. Now they must be heterozygous because they can produce 2 offspring which are homozygous recessive. So 3 and 4 heterozygous produce the homozygous recessive 7 and 9. Okay, and that's an explanation like so. Okay, so here's the mark scheme for that. 2 rhesus positive. Oh, I apologise for that. 2 rhesus positive parents, 3 and 4, have a rhesus negative child, 7 and 9. Both parents must be heterozygous and carry the rhesus negative allele. Okay, for the following question, 6.2, explain one piece of evidence in the diagram which shows that the gene is not on the X chromosome. Okay, for 6.2, it is not, explaining, again, one piece of evidence that it is not sex-linked. So we just go back to that one here. I'll do this in a different colour. Okay, so, again, if you look at page 13, and in fact, whenever we do these, if we want to explain that an allele is not sex-linked, well, there are 2 options. So, firstly, is the allele which causes that particular condition, is it dominant or recessive? And this time, we know that it's dominant. So, not sex-linked when the condition is known to be caused by a dominant allele we're looking for two affected parents, so affected, two rhesus positive in this case, producing, now a little bit more specific this time, unaffected or rhesus negative, now an unaffected daughter. Okay, so that's what we want to look for, two parents with that particular condition caused by the dominant allele, producing a phenotype in their daughter which is determined by the recessive allele. So here we have individuals 3 and 4 producing this daughter 9. So why is that? Well, if it were sex-linked, to produce 9, an unaffected daughter, the father would have to carry the recessive allele on his X chromosome. And that would mean that he were a rhesus negative male. Now that's not the case. Or if we think about that in a different way, we know that the father is rhesus positive. If it were sex-linked, he would have to have this X chromosome with the dominant allele. He would need to pass on that dominant allele to his daughter, and therefore she could not be homozygous recessive to be a rhesus negative female. So we've already proven that the allele is dominant. If we know that the allele is dominant, which causes rhesus positive, receiving that dominant allele from her father would immediately make her, regardless of what she received from her mother, that would immediately make her rhesus positive. Okay, so let's just explain that again. So explaining the evidence, again, this is a question about explaining. We're looking for two parents who are rhesus positive. Sorry, that's my dog. So rhesus positive, producing a daughter who was rhesus negative. Or two affected parents. When I say affected, try not to use that term, affected. We're looking for that, again, unaffected daughter. So when I say affected, I'm being very general. Really here we're looking for two rhesus positive parents producing a rhesus negative daughter. So 9 must be homozygous recessive, so must have inherited the recessive alleles from both parents. But 3, we know the male, I think I showed it on the wrong one earlier on, didn't I? 3, we know the male is rhesus positive. That means he must have that. If it were sex-linked, he would have to have that dominant allele on his X chromosome. He would have to pass that on to his daughter. So, if that were the case, all of his daughters would be rhesus positive. So, if the gene is on the X, then his dominant allele would be inherited by 9, so she would also be rhesus positive. Okay. So the second option for that, and I think I've explained both of these, if the gene were on the X, father 1, oh no, haven't explained that. Father 1 could not pass the rhesus positive onto his son. Yeah, that's another good point. Here, if this female is rhesus negative, if it were sex-linked, she would have to be homozygous recessive. The father would be would have the dominant allele on his X chromosome. Now the father can only pass on a Y chromosome to his son. The female can only pass on that recessive one. So if it were sex-linked, number 3 would have the genotype with a recessive R on his X chromosome and a Y. Okay, good. Now, I'm not going to look at the probabilities now or do anything with... Oh, in fact, yeah, I can do this probability. Sorry. What is the probability that the next child born to individuals 3 and 4 will be a rhesus-positive boy? Now, we know that this is not sex-linked, and we know it's caused by a dominant allele. We also know that these parents are both heterozygous. If that is the case, here we have our gametes. 3/4 of their offspring would show the rhesus-positive phenotype, because rhesus-positive is determined by that the presence of at least one dominant allele. What is the probability that it will be a boy? Well, that's a half chance, so 3/4 times a half is 3/8, or 0.375. Okey-doke. Sorry, this is the one that I'm not going to do. When we come on to Hardy-Weinberg, this is an example of a Hardy-Weinberg. A Hardy-Weinberg calculation using the Hardy-Weinberg equation. I'll go through that another time. Question 7 shows another pedigree. This time, question 7 is the inheritance of muscular dystrophy. Now, in the question, it tells us that DMD is recessive and sex-linked. Okay, immediately it's given us really important information. So, it's important for you to note that down. So it's recessive and sex-linked, or X-linked. Remember, all of these sex-linked conditions will be on the X chromosome. Therefore, for a female to have muscular dystrophy, she would have to have 2 X chromosomes, each with a recessive allele. For a male, he only has to have 1 X chromosome with that recessive allele, which is why it's more likely that a male will show muscular dystrophy than a female. So, first question. This time it asks us to give evidence to show that DMD is caused by a recessive allele. So we just go on to where is my... There it is. So here is the pedigree. Again, refer to page 13, but the evidence that something is recessive, we are looking for 2 unaffected parents who produce an affected offspring. Now remember, in the question, it asks us to give. So the command verb is to give. So 2 unaffected parents have an affected child, 8. So the response to this could be, oh sorry, I missed that one as well. Either 3 and 4 have 8, or 6 and 7 have 12. 3 and 4 produce 8, or you could say 6 and 7 produce 12. Both of those are fine, and they both earn you the 1 mark. Good. So that's that first part. Next, what is the probability that the next child born to individuals 5 and 6, where are we? Do we mean 5 and 6? Born to individuals. Oh no, sorry. Given numbers of 2 people who are definitely carriers of muscular dystrophy. Okay, now it tells us in the question here. No, it doesn't. It tells us up here that it is sex linked. So a carrier means heterozygous. If it's sex linked, only females can be heterozygous. So we're looking for 2 females who are heterozygous, and we know they will be heterozygous if they can pass on a recessive allele to a son to produce, to give that son muscular dystrophy. So we know that the definite carriers must be number 4. I'm going with R's again. Doesn't really matter what you use. Number 4 must be heterozygous because she passes on this recessive allele to her son, number 8. And number 7 must also be heterozygous because she passes on her recessive allele to number 12. Should have done it on here really. Okay, so 4 and 7, both unaffected mothers who have affected sons, they must have passed on the recessive muscular dystrophy allele to their sons on the X chromosome. So like we said, 4 is a carrier or heterozygous, 7 is also a carrier or heterozygous. They pass on their recessive alleles to their sons. Fathers cannot be carriers, so it can't be 3 or 6, as they have the, if they had the recessive allele on their X chromosome, they would also have the condition. So we know that 3 and 6 must have the dominant allele. Oh, whoops, that is a Y and not another X. Must have the dominant allele. Let's draw that again. On their X chromosome. Right, last part of this question then. Which is, I think it's 7.3, not 8.3. This is from the old booklet, yeah. So complete the genetic diagram to find the probability that the next child of 6 and 7 will be a son with muscular dystrophy. Okay, so from our previous explanation, we know that number 7 must be a carrier. Okay, so I'm just going to add a new slide in here. So number 7, the female. Let's just move this along. And number 6, the male. Number 7 is a carrier, so she is 1 dominant and 1 recessive allele. Number 6, well, he doesn't have the condition, so we know he must have the dominant allele. What is the probability that their next child will be a son? So, number 6, unaffected. The parental genotypes. I should have done this the other way around, really. Parental genotypes. 6 or 7, yeah. The gametes they can produce. Remember to draw the gametes in circles to make it really clear that they are gametes. So they can either produce, or the male can either produce an X chromosome in his gamete with that dominant allele or a Y. The female can produce one or the other. Okay. The Punnett Square, if you lay that out, would look something like this. That's the dominant one, and the recessive one. Let's see if I can draw a straight line here. I'm getting better at this. Okay, so this is a female, homozygous dominant, and therefore no muscular dystrophy. This is a male who is with the dominant allele. This is a female carrier, and this is a male with muscular dystrophy. Now, as this is a sex-linked condition, we don't need to multiply it by half because we've already got the both parts of the phenotype there. So male with muscular dystrophy. So the probability would be 1/4 or 0.25. Okie doke. And there we go. There it is, all a bit neater. I think I will call it a day there. In fact, the next question, question 8, I have made a video about this previously, and if you dig around on the channel, one of the very first videos I made years ago is this one. So you can watch that if you want to, or have a go at it yourself first. Hope that was helpful. Remember, email me if you need to. But all the best. Take care.